Good morning or good afternoon to everyone, wherever you may be. My name is Anthony Price. I'm the current chair of the Regional Advisory Committee for the SEG Europe. And I'd like to welcome you all today to the webinar series of the RAC Europe and introduce our speaker today, Gabor Tari, who's the Group Chief Geologist at OMV upstream, currently working in the Business Development Division, and previously he was the Vice President of Geosciences at Vanco Energy in Houston. So without further delay, I'll hand you over to Gabor. Thank you. Over to you.
Thank you, Antonio, for this brief introduction. It's really a privilege to present the CEG event. I have to say that I have a degree in geophysics, so that perhaps gives me a little bit of credibility to be a speaker here. So let me share my screen, and then Antonio, you tell me if this is working or not. So thanks again, and the plan for this afternoon or for your morning is that I will talk about for 45 minutes, and then we could perhaps go to a Q&A. As a general disclaimer, I have to say that if just because I'm presenting today, it perhaps sends a message that I'm an expert on the topic. I was working on it for 4 years now, but I have to say that there's no one who could claim that really he or she is an expert in this field, because it's such a new field. So what I can convey today is some personal impressions or experiences, and then we all hope that we, as geophysicists and geologists, will get a better and better understanding of this topic, which just came out of left field, so to say, in the last few years. So this is what I'm going to talk about, just very broad outlines, a little bit putting the natural hydrogen in a context in the energy transition. And then I will take you on this quick virtual field trip to a very exotic place in Mali, West Africa, which turns out to be a very key point for the story. And I will talk a little bit about the similarities and the differences when it comes to natural hydrogen exploration, if we compare it to what we are all used to, and that is oil and gas. And all along, I try to highlight some geophysical aspects, because it's the SEG here, and you guys are more interested in those aspects rather than me talking about chemical, geochemical and other aspects, which is a totally different facet of this natural hydrogen storyline. So just a brief reminder to all of us where we stand as humankind, and I wish I had the image here at the bottom from 2025. But the image speaks for itself. We just want to have more and more energy, and that is a big challenge for all of us. And what if we look ahead? And I took this slide from a friend of mine, Mike Simmons, who made his calculations, and this is what he came up with. How would it look like, the global energy mix in 2050, assuming rapid energy transition, if we can go through it? And without going into details, of course, very importantly, we will still have oil and gas, and nuclear will getting stronger. Hydroelectric cannot get much bigger than as is, and coal, again, we need to phase that out. But here on the left-hand side is a big group, which generally speaking are called the renewables. And within this big group, there is this item called the hydrogen. And that's really the dark horse for all of us, what that item will do in the next few decades. And of course, colors, when it comes to hydrogen, we have the whole rainbow. And without going into details, there are a lot of different varieties of man-made, artificial hydrogens, and I don't have to spell this out. But at the very bottom of this compilation, there is a category which is called natural, if you will. And within this, there is geological or gold, some people call it the gold or natural white hydrogen. And there is this bacterial / stimulated orange hydrogen. Some people phrase it differently, but this is a good enough first subdivision for us. And I'm going to talk about mostly about the natural or white hydrogen today. This is a very good summary published by Ossel in Nature in 2021. And it shows this different kind of colors of hydrogen made artificially from different substances. But again, here are the kind of natural ones. Truly natural one is the white hydrogen, which we are supposed to find in the ground. And there is this orange hydrogen type, which is a stimulated, like a resource play type hydrogen, which is a very interesting topic on its own, but we might not get into it today. I will focus on the purely natural hydrogen species. Just one more word, though, about the orange hydrogen is that there are rocks, and this is the part which I'm not going to get into any great details. There are rocks which could be induced to produce hydrogen if you put them into an autoclave and then you put them in certain temperature and certain pressure, then they start to produce hydrogen. And this is typically rock types which belong to the ophiolite group in general speaking. And then, for example, in this case, Harzburgite from Cyprus, which I collected, clearly shows the signs of going through this process naturally. If you look at this vein, which is a serpentinite mineralization, and then what people call the Frankenstein fractures, you see these little very fine fractures radiating out from the big vein perpendicular to the host rock. This shows that the serpentinization was ongoing or still is ongoing in this particular domain. So you could have hydrogen out of rocks, and it's not just ophiolites or serpentinite in particular, but there's a whole list of rocks and settings where you can expect natural hydrogen. And again, I'm not going to go through this list, but a compilation, and then many people show these days compilations from different data sources all over the globe. Wherever you go, you find historical reportings of natural hydrogen. And just to kind of cross-check this, we also try to see whether we could repeat these compilations, global compilations. And a friend of mine, colleague of mine, did the same thing. And indeed, looking at pure G&G industry data sets, mostly industry data sets, one could come up with a quite wide distribution of hydrogen finds in gas. And if you look at the size of these bubbles, you could see that some of these finds reported quite high percentage of hydrogen in some kind of gas in the underground. So this is very important because it tells you that hydrogen has been found in the past since we drill for hydrocarbons, but we never really paid much attention to it as an industry. There was no need to do that. And I make the point many people did make earlier, especially Vyacheslav Zgonik, who made the very first compilation like this, is that you see a bias towards the former Soviet Union, if you will. And this is not driven by geology, but just sheer fact that in this region of the world, there was a more deliberate tendency to measure all kind of gas components in a gas mix, including helium and hydrogen, and therefore you have many more hits in the former Soviet Union or Eastern Europe, if you will. Now, let me take you to this singular large bubble, which implies that somebody found a very high percentage hydrogen in a gas mix. And this is what I told you at the onset, that this is a kind of a cornerstone case history, what has been found in Bouraké-Bougou in Mali. And it's a very interesting find because many times, like even in our profession, people were drilling for something else. And in this case, they were drilling for water back in 1987. when they accidentally found a gas, and you probably heard about it many times over by now. I just quickly repeat that they were very surprised when it turned out to be this odorless, colorless gas hissing out from the wellbore is 98% hydrogen. They found at from coming up from a relatively shallow depth of 112 meters. And then they didn't really know what to do with it, but they came back much later and they did a proper drilling campaign. And sure enough, in all the wells, and they did drill more than 24 wells, they found the same thing, a very high percentage hydrogen coming up to the surface in a fairly large area, in an area which they reported to be at least 780 square kilometer. That is large. And when they really analyzed the well results and the geology, turned out to be very, very bizarre, if you will, the whole storyline. And one is that the reservoir was very, very old rocks, Proterozoic in age. And then the gas finds in multiple levels in these very old rocks, they turn out to be sealed by dolerites. But these are probably Triassic age basalt dolerites, which you can see in outcrop like this. And these dolerites were able to hold back these hydrogen pools in multiple levels. So this looks a little bit strange. I think we all agree that at this relatively shallow depths, this is not exactly looking like a gas field. But if you look at the numbers, in general, it does remind you like a regular natural gas field. So people claim that this could be potentially a 50 to 100 BCF hydrogen accumulation. And then from one well, the production is in the scale of 46,000 scuffs per day, not too bad. The pressure, of course, is very, very low because we are very close to the surface. But strangely enough, after this production, it doesn't seem to drop, but rather increasing, which is already also a strange thing on its own. And then they produce this one well, and again, 5 years, stable production, and no signs of depletion. So this is a very, very interesting find. And of course, and I got these images from Mr. Hydrogen, Professor Prinzhofer, who was very close to this whole storyline. And it's really a very interesting find because there is a case now where people can claim that there is a hydrogen field on the planet, but unfortunately, it doesn't really provide a business case for us because it's located in a very remote place next to a small village. And as we all appreciate, Mali has other problems these days than trying to develop a hydrogen field. So we cannot really use it as to argue that there is a up and running business where people make money by producing hydrogen. What they do here, they produce just one well, and they use that hydrogen in a little engine to produce electricity for the village. That's all there is to it. Now, still staying with Professor Prinzhofer's pioneering work, he was the first who started to compare the hydrocarbon systems on your left-hand side with the hydrogen systems, if you will. And I don't want to go through all the details, but if you look, they are very, very different. And before I go into some of the differences, let me make a general statement, which I like to emphasize, is that some of us in the hydrocarbon business like to think that we could just move very smoothly over to this new field of hydrogen exploration, having the exact same same mindset, the same tools, the same risking, the same tools in our war chest, and it's going to be just the same. And quite frankly, I don't think it's a good idea to look at hydrogen exploration like that. The more I look at it, and I think many people share the sentiment, the more differences we do see, the way we have to approach natural hydrogen exploration versus hydrocarbon exploration. And some of the elements for the difference are captured in this diagram. These are very different systems. And just to highlight a few, the the hydrocarbon systems are really very static and largely static systems. And then, as we all appreciate, it takes millions of years to have an accumulation put in place from a source rock maturation and then migration and all those things. Again, it takes a long, long time to have a field accumulated, and which is very, very different from the hydrogen system, which is a very dynamic, very quick system where you could have relatively quick generation and very aggressive or efficient migration to a temporary trap. And therefore, coming back to this last point, we don't seemingly think too much about seeps dealing with hydrocarbons. And of course, we like to have them here and there. They are nice giveaway. We typically don't like them though, because they would tell us that the trap is compromised. As opposed to the hydrogen systems where seeps are the bottom line, the typical everyday experience. And the scale of seepage, if you look at the numbers, is order of magnitudes larger for hydrogen systems than for hydrocarbon systems. So that's a big, big difference, which, as I'll show you later, has to translate to a very different way of approaching the exploration for hydrogen. Now, this is a kind of a little simplified, and I'm sorry if I offend anyone with these simple cartoons, but perhaps they tell the story. On the left-hand side, we have cases of hydrogen, where we have the same elements or the same feel to it, like like for a hydrocarbon situation, and I will show you some examples, like in salt basins in Australia, or in this case, I'm quoting Ukrainian example, and I'll show you the Ukrainian example, is that you do have hydrogen accumulated below salt in a trap which you call pre-salt. And this is very, very familiar from the hydrocarbon business. I'll show you the West African Mali example, which is, as I showed you, is a little bit different in the sense that we are typically don't work with dolerite seals. I'm sorry, this water shouldn't be there. It's a very tight dolerite which holds back, is able to hold back the hydrogen from getting through. But this is a trap, and then basically the story is about drilling into a trap and then producing hydrogen out of it. So this we can relate to. And then the question really is that how fast the accumulation would be recharging, and are we looking at finite resources if the recharge is fast enough? And people lately argue that unfortunately we cannot really expect a fast enough recharge. So we could claim that it's going to be a sustainable production. It's unfortunately not the case. We'll probably end up finding hydrocarbon fields like this, and they're going to have a finite amount of production time down the road, and we'll be done with them. Now, in this context, it's perhaps more exciting or more like a brave new world, what I show you on the right-hand side, because these items here on the right-hand side are very specific to hydrogen exploration, and they don't find their counterpart in the oil and gas business. And that is the large seeps, which I'll show you a couple of examples of, the fairy circles, if you will. And these are not themselves exploration targets at this point of time, but they show you that you are in the right place, and then you have an active kitchen, so to speak, where you are. And the other category is faults, large faults dissecting, for example, ophiolites, like in the case of Oman and New Caledonia and many other places in the world, where you do have very pronounced seepage to the surface from a kitchen. The hydrogen is coming up, and it likes to find places where it can migrate even faster towards the surface, and that is fault plains. And then the question for these systems is that, okay, we have active charge, we have dynamic system. If it's a steady state migration and generation, which we can assume it is, do we really have infinite resources if we are not too greedy, and then we are happy with capturing whatever small rate of hydrogen we have. And is it going to be commercial if it's just such a small rate but steady rate, which will go forever? And these are questions we don't really have the answers to just yet. Now, I'm going to talk about first on the items on the left-hand side, show you some examples of this kind of approach, which is very similar to what we are used to in oil and gas. And our French colleagues were very good pioneering this mindset of starting to look for hydrogen specifically. And they did that in the French Pyrenees. And this classic oil and gas province in the French Pyrenees, and it's four deep, is very well known with big fields. And now it's being relooked in the context of finding hydrogen in some reservoir units. The way it's shown is above the salt. It's not below the salt, but above. So it's a little bit different from what I've just showed you. But this is a valid play, and we're going to try to test it hopefully in the next few years. There is an even more ambitious version of this area where they would actually drill through the salt and try to go to the source, which is down below, and it's a serpentinized mantle body. And this would be ideal, of course, the depths of this exercise, the way it's shown, tells you that it's going to be a very, very expensive exercise if it happens. But of course, technically, it would make a lot of sense to go to the source, literally, if you will. Now, I mentioned very briefly Ukraine and salt, and then the pre-salt traps. This large Dnipro-Donetsk area, which you keep hearing about on the news every day almost. It's a classic large super basin, in fact, for petroleum. And a lot of gas has been found in positions like that. And our Ukrainian colleagues reported for the longest time that is just not just natural gas, but it had all along many wells, a lot of hydrogen in it. So that's why I show this little hydrogen gas cap, if you will, sitting on top of natural gas. And sometimes this proportion of the hydrogen, they report up to 20-25% in that gas. So the importance of this cartoon, and I like to make these very simple-minded cartoons to tell the story easier, is that the gas, the natural gas is coming up from below the basin, from the Sindrift grabens with the usual salt stroke we are used to. But the hydrogen is coming up from the crystalline basement because it's produced by radiolysis. And the interesting point here I try to make is that our Ukrainian colleagues found a lot of gas below these large salt bodies in the center of the basin. But towards the basin edge, the basin margin, if you will, they found many times that there's no accumulation. And the reason is very clear, because there is no major Sindrift source down below. So you cannot really expect natural gas accumulation. But if you approach it from the natural hydrogen point of view, then you could argue that, well, it doesn't matter, because the basement, the crystalline basement, which is generating the natural hydrogen, is down below. You could find perhaps hydrogen accumulations at the basin margin. And this is a case of trying to show that hydrocarbon systems versus hydrogen systems might overlap spatially. And this is another case, total speculation on my part, but the Cyprus is very well known for the famous ophiolites. And then many of the springs you could see on the surface in the Taurus Mountains, indeed, hydrogen has been observed. And this is a result of the serpentinization of this ophiolite succession. That's how the hydrogen is being generated in this setting. But interestingly, you probably heard about the big gas finds by the ExxonMobil's, ENI's, and Total's in the deep water part of Cyprus, which is became a classic hydrocarbon play fairway. But people don't follow that further towards the coastline because there is no sediment pile with the source rocks underneath the Messinian salt. But this is the part where you could expect potentially hydrogen pools below the Messinian salt in situations like that. And from a geophysical point of view, the takeaway here is that there is a lot of data in the deep water for obvious reasons, but there is very little data or seismic sections in the shallow water or the, let's say, even transitional zone because people never saw that this would be prospective. But perhaps, and I'm saying just perhaps, this is a case for a speculative hydrogen play fairway. All right. So this could be another case where the hydrogen play fairway is overlapping, a little bit overlapping with an existing and well-established hydrocarbon play fairway. Now, one more item before we move on from this standard situation of expecting hydrogen traps below salt or evaporites. Another case from Ukraine. We do consider the evaporites in general being the super seal, not only for hydrocarbons, but also for hydrogen. This really works most of the time, but there are some cases where we do see some indications that if your evaporites are not very thick and they have a certain compositional challenge, shall we say, in this case, these are mostly anhydrides, then perhaps through time, hydrogen and helium is able to get through. And this is a story, again, from Western Ukraine, where the data suggests that hydrogen is able to get through to a certain extent, even though not perfectly, but through time, even evaporites, certain evaporites may not act like superseals. Now, this is the part where we switch to that other side of the cartoon diagram I showed you earlier, this brave new world of features which are specific to hydrogen, these fairy circles, which became the poster child of hydrogen exploration, for better or worse. It's worth to spend some time on these things because even though they may not be the exploration target per se, but they tell you that you're in the right neighborhood when you explore for hydrogen in the subsurface. And from a geophysical point of view, the very interesting storyline here, and I lifted this text and reporting and image from a Ukrainian website describing this early find by some Russian colleagues. It's an interesting compilation because the fairy circles are very subtle but very well expressed vegetation-wise, subcircular depressions. And then the giveaway for the hydrogen fluxing in them is that you start to measure very simply the content of hydrogen in the soil in a depth of just a meter. And I'll show you a lot of instruments which can do this for you lately. And then outside of these fairy circles, you don't have any signal. The hydrogen is zero, practically zero. But once you are within the fairy circle, then the signal kicks in and it goes up to the few hundred ppm to 1,000 plus ppm range, which intuitively tells you that there is a hydrogen flux from below, which is clearly causing the fairy circle itself. And our colleagues quote a microseismic sounding device, but they don't really describe what it is. But in their interpretation, in their mindset, in the former Soviet Union, there is a strong belief that most of the hydrogen, if not all of it, is coming from the deep earth, and it's basically the manifestation of the degassing of the earth, and this is what they would tend to call the primordial hydrogen, which is trying to get to the surface. I couldn't find any more documentation on this diagram, but the scale is staggering because it's going down to 20 kilometers, and the scale horizontal is 5.5 kilometers, and then the color scale is decibel, in decibel, and it shows if it's really the way it has been processed, that there is a pretty much a pipe-looking thing, which could represent the gas, in this case, the hydrogen coming towards the surface really in this vertical manner. Very interesting statement, very interesting mindset. Again, there is a geophysical component behind it, but I won't be able to document or show you exactly what this microseismic sounding device did. Now, staying with the fairy circle topic, another classic area after Russia became Brazil, where Professor Prinzhofer did a lot of work with some other colleagues, Isabel Moretti and many others, basically recognizing the same phenomena. There are these big subcircular areas, really large ones, and the small ones superimposed on them. Sometimes just a few hundred meter across, sometimes even a kilometer or two. And they are always very shallow depressions, and they always have what people call the vegetation damage. You could see how drastically the vegetation changes in these units. And there were many other interesting things people found, and I will talk about it briefly. Observations made on the surface, surface being the first 1 meter from the surface in the soil. And it seems like putting down these sensors, which measure the hydrogen concentration in the soil throughout the day, day after day, clearly it's a system which is breathing. And there's a daily variation. And then you ask yourself how much it is generated by biologic processes, how much it is truly geologic hydrogen. What I don't show here and what they documented, there are some certain bursts in this pattern, which tells you intuitively that perhaps there is a big signal coming down from below and then kind of destroying this pattern and corresponding really an active hydrogen bubble, a big one, if you will, coming through and then trying to find its way towards the surface. And then I was trying to think whether we could explain the vegetation damage in this circular manner. And the very logical explanation, looking for an analog, is to find a vegetation damage associated with leaking pipelines. But this is like dirty laundry. You don't find many examples of this digging into oil and gas company archives because of the legal implications. But I found this PhD from the UK, very nice work in 2002, where this lady did a nice study on the vegetation damage associated with a very old Victorian 12-inch cast iron main, which is still active. I used to supply coal gas, talking about hydrogen, but now it transports natural gas. And then the barley, which is growing over this very old pipeline, tends to get damaged right above the inferred joint points. So if you look through this work and perhaps some other works, then you could convince yourself that the vegetation damage is really corresponding to a point source, in this case, from a leaking pipeline. And then by inference, you could argue that the fairy circles, the way we know them, are also corresponding to gas coming up from a point source from below. And a colleague of ours here at the Vienna University just published a paper in geology where he shows a modeling study assuming mechanical compaction. And his storyline is that if you assume certain a gas input from below for a while and then you shut it down, you could reproduce the overall geometric depression of the fairy circles, and you could also explain the gas flux, which is typically measured in these fairy circles by many. So I put this together a couple of years ago, and perhaps I could still look at it like this, but collectively we don't really have a good understanding how these fairy circles work in the subsurface. On the surface, it's fairly well documented by many, but how this relates to the subsurface, is it really true that we are looking at an inverse cone where hydrogen is getting dispersed and then produces this hydrogen signal on the surface. I believe that this might not be a bad idea if you believe the analog I showed you from the pipeline leakage. And then you can see some numbers, and then these are numbers which were reported, for example, from Brazil. This is how much hydrogen you could expect per day per square kilometer. Now, this number might not be very large or impressive, but you have to think about the filtering effect of the soil. All right. The point here is that from a geophysical point of view, the subsurface imaging is missing. We don't really understand what's below these fairy circles. And as far as drilling, there was just one drilling attempt in Nebraska to drill straight into a fairy circles, and the results have not been published in any great details since then. Now, talking about geophysics, you ask yourself, what else can be done, or do we have an analog, a tool in our geophysical war chest, which we could use to specifically go after gas coming up to the surface in a supposedly conical shape? And interestingly enough, people do study CO2 seepages or morphettas, and this example comes from the Czech Republic. And it's a very nice work in the sense that they did go through an exercise of putting sensors out there. And it's basically a seismic noise measurement. And then they didn't even run it for very long. But the result of this thing, and you can look at the depths down to 20 meters, it's a very different depth scale from what we are used to, is that the signal, the CO2 gas coming up to the surface is really showing the same kind of overall inverted conical shape, what I just showed you before. And it does come up in a subcircular manner on the surface. This is the scale here. All right. This is just to show that this is a dry morphetta. It is a dead bird there, so it is a typical morphetta. And the reason I'm showing this to you, because we do have some analogs from other fields, people going after morphettas, going after CO2 with geophysical tools. But geophysical tools we don't use typically in oil and gas, but here they are and they exist, and they are pretty effective the way it has been shown. Now this is the part when I'm switching to some other tools. These are not geochemical tools, they are closer to kind of physical measurement tools. So let me just call them geophysical tools in that sense. And I never thought that I would be very interested in making soil gas measurements in 1 meter depth, but here I am. And it's amazing to see that how many instruments were put on the market in the last few years, driven by the interest in natural hydrogen. And there are the monitors, a lot of devices which measure instantly the gas composition in the soil. But this is really a space which is developing very, very quickly, a lot of innovation involved. It's not just that you do point source measurements at a single time, but people came up with instruments like this instrument developed in University of Po, which you can leave on the ground, and then it works autonomously, and then it can measure the hydrogen content in the soil at 1 meter depth in every minute. And you can leave this machinery there for weeks to measure the signal, which ends up looking like this. It's very much like the Brazilian example, but it's a high resolution product, and it shows the same reading system and some correlation with the air pressure and temperature and many other things. And I'm not here to claim that this is for sure the expression of a hydrogen system down below, but this is a result, this is a tool which you have to have in order to start somewhere and try to establish that you are in the right neighborhood. So the other element I showed on the right-hand side of that introductory summary figure is this, where I started to talk about faults. And again, coming back to our French colleagues who did very good pioneering work by emphasizing the role faults could have in conducting the hydrogen along their planes. And this is a nice case study from the French Pyrenees, where they put sensors in different places, but one sensor they put expressly, decidedly on a relatively large fault. And what they found is that the fault really conducts the gases, not just hydrogen, but methane, radon, and CO2. And the hydrogen signal is shown in yellow in particular, and you can see that it's a logarithmic scale on the left-hand side. So basically, the storyline here is that the fault is acting, to quote Professor Prinzhofer, as the highway for all the migrating hydrogen, as opposed to the rest of the neighborhood, which doesn't see much action at all. So faults have a really important role to play in focusing and delivering and conducting the hydrogen towards the surface. Now, just a quick side note, every company has a big data set. And for example, in our case at OMV, we just looked at very quickly what kind of hydrogen reportings we have here in the Vienna Basin. I'm sitting right here by now. And these are big faults in the Vienna Basin, and this is the depths of the basin Neogen depth structure. Sorry for the details, are not really important. What's important is the outline of the major faults, major Neogen normal faults. And what's very interesting is that, generally speaking, or some thrust faults, is that there is a loose correlation with some faults across the basin. Not always. Here's a big field, the Madsen field, and it doesn't sit on faults or major faults anyhow. But seemingly there is a correlation in our view between the hydrogen anomalies and large faults. Now, as a side note, I have to say that it's really tricky though to take legacy gas reportings, because as you are all very aware that many times there are false signals. You do have, for example, in our case, many people noted the detonation gas when people did sidewall core tests, and then you do see a strong hydrogen signal. And of course, you have production wells where the corroding steel casings can also produce hydrogen. So these numbers are sometimes misleading, so you cannot take them literally. But still, sticking with the fault pattern, the fault theme, what you can see here is the importance of fault planes conducting gases. And this is very nice work from a small French company, 45A. And these guys went specifically after very, very shallow faults, which conduct not only hydrogen, but in this case, their main target was helium. And these are these boiling fountains, boiling wells, if you will. This is how they know that, how they knew that they are the right neighborhood. And the geophysics which was involved, and I'm not showing many examples here, it was really literally trying to understand exactly how these shallow faults look like in high resolution. There are other ways of and this is about geophysics, how to locate faults, fault traces on the surface. This is back in Brazil. And this example is really just showing the tool. This is from Canada. That these days, of course, you could put the gamma spectrometers either on drones, or you can walk through the terrains like they did in Brazil. And you can have very good maps showing the fault plane or inferring the fault plane by the thorium and uranium response. So this is pure geophysics, and it's not even a very expensive tool. If you cannot shoot seismic in the neighborhood, this is a very first tool to use. So in general, what I do see is a tendency to have a closer look at faults in general, because if faults really do conduct hydrogen, in a very efficient manner. Perhaps there is a case for a hydrogen farming scenario. It's a little bit reminding me the geothermal storylines where people are willing to drill very shallow wells in their backyard. And in this case, they may not collect hot water, but they might collect hydrogen if the aim is very good, and that you can hook up individual very shallow wells being 100 or 200 meter deep. So this might be an interesting direction, which again requires geophysical approaches, which are very specific to the shallow level. And just to sum up this part of the thing, and we are coming to an end soon, is that the hydrogen exploration mindset, I think, is going to be quite different from what we are used to. The faults will have a very important role to play. And then you really have to think where the hydrogen comes from and where it migrates. I don't show any modeling attempts here, but the physics of hydrogen migrating is very different from that of oil and gas. Still staying with the geophysical theme, how do we handle the serpentinites, which are the kind of the generating rocks of hydrogen? And what I do see is classic geophysics coming back. And what I mean by this is that potential field modeling of magnetics and gravity, sorry for the misspelling. For example, in Austria, when we saw these serpentinites on the surface, I really wanted to know how deep they go and what's their overall subsurface geometry. Nobody really cared about this beforehand. But now, by modeling these things, we do see a case for having a certain specific underground geometry for these Peninic serpentinites, which at certain depths, 3, 4, 5 kilometers, expected to produce hydrogen. And this is a very nice work which just came out dealing with a famous case of an Albanian chromite mine, where folks recorded a large amount of hydrogen coming into the mine, and then the mine, unfortunately, sometimes having accidents because of that hydrogen detonations in it. But the method they used to have, here's a classic geophysical method, MT. And with the MT, they were able to show the overall body of the serpentinite because of the resistivity, and beyond that, they were able to kind of infer how much the serpentinization progressed. The more serpentinization you have, of course, in the process, the more hydrogen you're going to have. But you don't want to exhaust your serpentin to the point that it has nothing left in it. But in this case, they clearly showed that there's a nice case for active serpentinization at depths, is the depths, and you can see that this explains why hydrogen is coming to the mine in such a dramatic fashion. And just very briefly, and coming to the end, is that the business angle for hydrogen is that not all hydrogen finds will work in a competitive manner. If you have the hydrogen concentration less than 5%, then just the separation cost is such that it's not going to compete with blue or green and other kind of artificial hydrogens, just not. So you really need to have, to make it very simple, a hydrogen mix, a gas mix which has hydrogen more than 10-20% minimum. And this is just the nature of the beast, because at the end of the day, we are competing with man-made hydrogens, especially with green hydrogen, which becomes a very, very strong product on the market. All right. And again, the competition, this is not a very hard field of competition just yet, because nobody came through really successfully. But this is a field which I think is going to see a lot of action if somebody comes through with the discovery. And this is my last slide. And sorry, I'm talking a little bit too long. And this is a colleague of ours, Eric Gaucher, who very smartly came up with this concept of likening the point in time where we are as the tipping point for natural hydrogen exploration, pretty much driven by the Mali discoveries and comparing it to the classic tipping point for oil, our classic profession, which was driven, among many others, but this is a particular case everybody knows, the discovery made by Colonel Drake in Titusville, Pennsylvania in 1859. And that just triggered a huge thing. And perhaps, and again, just perhaps with some question marks, this Borokabubu discoveries in Mali will be looked at the same way a few decades down the road. So this should be my last slide, and I'm going to stop. Back to you, Anthony.
Thank you very much, Gabor. That's a very interesting overview of the subject. You've certainly done a lot of work on this. Okay, so we have time for some questions. I'll start by going through the questions in the Q&A box. Please, if you have any questions, it's not too late, please post them there and we'll try and get to them all. The first question comes from Diman Mujamder. Sorry if I mispronounced that, asking, are all ophiolites associated with hydrogen?
That's a very good question, because some ophiolites didn't read the textbook and they don't have these very ultramafic elements in them. And therefore, not all ophiolites are created equal. It's probably a shade of grays. But to answer your question, not necessarily all ophiolites will deliver the required hydrogen flux, A. And also, many ophiolites tend to be found in very small, volumetrically small pieces, kind of dismembered, either very thin or area not very big, and then close to the surface, meaning that they are not producing anymore. And those conditions will disqualify these ophiolites from being a target. So one has to look at it kind of in a wider context, and not all ophiolites will be candidates for exploration.
Fair enough. I'd like to actually add a follow-on question while we're on the subject of ophiolites myself. It's more towards the ultramafic part of it, but the serpentinization route can be a generator for hydrogen. But as far as I understand it, you need very somewhat specific temperature and maybe pressure regimes to make that happen. Could you expand on that for us?
Yeah, temperature is very, very important. And if I want to compare it very briefly to oil and gas, we like to put our source rock in 100, 200 Celsius temperature range in order to generate. The numbers are bigger for serpentinites. You can put them down in greater depths, greater pressure, and temperatures down to 400, even 500 Celsius. And their generation range, if I want to make it very simple, is deeper and hotter and higher pressure than what we are used to in the hydrocarbon business. So the best optimal generation for hydrogen from a serpentinite is I just quote a number between 200 to 400 Celsius ballpark.
Okay, thank you, Gabor. We have a question here from Tim Papworth asking, what are the best ways of detecting hydrogen seeps at the surface? You showed some examples already, but perhaps you could expand on that.
Very good question, and it really depends on your budget, because these soil gas measurements are the cheapest and easiest, and you can have students go out and do it for you. And this is what we did, quite frankly. But it comes with a headache of not knowing exactly whether you are picking up on a biological signal or a real geologic signal. It's going to be a mix. You want to do isotopes. You want to look at other gases. You want to measure certainly other gases other than just hydrogen, CO2, helium, nitrogen, and all the likes, which makes the whole process more expensive. But then you could really convince yourself that you do have a real natural hydrogen seep from the deep. So it's really all about the budget you have. Now, generally speaking, satellite work not going to help very easily. Some people claim that it's piece of cake. There is unfortunately some cases of voodoo geophysics where people claim that this is nice and easy to detect hydrogen. I don't share that sentiment. But there are some other methods, like people in Australia published a nice paper. They have a LiDAR technique, and then even Ukrainian colleagues have a LiDAR tool which can detect hydrogen coming to the surface. It's not easy, and it's not a cheap solution either. Other techniques like drones flying over the terrain, and Chinese produced detectors which can pick up on hydrogen. But in our experience, when we tried to do this, it's not working, or it didn't work for us because the drone blows the air away, and then many other things. And you have to be very, very close to the surface if you want to catch that hydrogen. So that is not working. So there's no really easy way to find hydrogen seeps. You have to consider a lot of things, and you have to do a lot of work, and you have to do a lot of gas work in order to land on a real bona fide seep. And of course, there is this nomenclature problem, is that experts like Professor Etiop doesn't like to call these things seeps, because to him, seeps is a different category. So let's call them micro seepage of hydrogen, and these are again very hard to nail down on the field.
Okay, thank you. We have a question from Nicholas Nogin asking, how can we explain the variation of fairy circle diameters from very numerous but very small, couple of meters only, like in Northwest Australia, or to very large circles, 2 kilometers across, as you show in your Russian example on slide 19?
Yeah, very good question. Everybody should have, myself included. Of course, intuitively, it would be nice to say that either it has something to do with the depth, or the flux, how strong the flux is, and has something to do with the basin cover, what you have, the lithology of the rocks involved. I don't have a simple answer to it, but we have some guesswork coming out from this numerical simulation my friend and colleague Martin Schöpfer did at the University of Vienna. Perhaps you could infer something about the subsurface point source, the depth of it, using the size, but we are not there yet to be absolutely conclusive.
Fair enough. We have another question from Diman Majinde asking, and I noticed this too, actually, in some of your direct hydrogen measurements at fairy circles, for example, or even the faults, there seemed to be a diurnal variation. How would you explain that?
Yeah, very good point. This is an ongoing debate in this natural hydrogen community, is that how we can separate the biological signal, the fermentation ongoing in the soil versus the real geologic signal. And I mentioned Professor Etiop, who correctly says, and then others agree, and we all try to implement this, is that we have to look at it holistically. We have to look at other gases as proxies. And then, as Professor Prinzhofer does it, you have to have a good understanding of the gas composition. Nitrogen is a good indirect giveaway for having possibly a real geologic hydrogen gas. And of course, helium likes to go hand in hand with hydrogen as well. So you can have proxies, which could suggest that, okay, you see the diurnal variation, but this is just a small biological signal, but it should not be the case for throwing the baby out with the bathwater. There is an underlying geologic signal which you don't want to walk away from just because you see daily variation.
Thank you. Gabor, are you happy to continue with questions, or are you?
Yeah, absolutely. If there are questions, by all means.
because we have a lot of questions. There's a lot of interest in this subject. I just quickly, there was another question. We've had a few on getting a copy of the presentation. There should be no need. This is being recorded and it would be posted on the SEG YouTube website eventually. So you'll be able to rewatch it there or watch it if you missed it. There's a question from Robert Lorenzen asking the various circles that you showed on slide 23, originating from deep fault plains. How would these seeps become circular from along the fault plains?
Well, what happens is that along the faults, there are places where the hydrogen is able to depart from the fault plane and then becomes a point source. And then Australians claim that this actually happens along faults in the Perth Basin. There's a paper by Emmanuel Ferry who published this, and then they say that basically the fault plane is being tracked by a bunch of these ferry circles. So the hydrogen can depart close to the surface from the fault plane itself, and then it manifests itself as a string of pearls, if you will, showing indirectly the underlying fault. I hope it's an answer.
I guess there's small scale geometry that may be governing that. We have a question here from Maha Ali Haider saying that he's more concerned about how we would distinguish the source of hydrogen and how would we know from where it is coming from. So in your opinion, is the major source of hydrogen radiolysis, pentonization, or other mechanisms?
This is relatively easy because the regional geology, luckily we know as a community, industry and academia, anywhere on this planet, we know quite well what kind of rocks are underneath. Either we are sitting on a crystalline craton like the Ukrainian shield or the Brazilian shield or West African shield. In that case, we know that we are dealing with crystalline rocks. We are going through radiolysis, or we are sitting somewhere in the semi-arid ophiolite in Oman or Abu Dhabi, or in New Caledonia, beautiful ophiolites, or somewhere in Europe. There are plenty of alpine ophiolites, and then we do know that if we do have a signal for hydrogen, it has to come from the serpentinization. So this is relatively easy to answer. Again, the answer is in the existing knowledge of the local and regional scale geology.
So I guess the context is what really tells us what the sources might be.
Yeah.
Fair enough. Okay, we have a question here from Luis Venego, stating that, 2D and 3D seismic are the main tools for oil and gas. And he's asking whether they would also be tools for exploration for hydrogen. I guess you showed some sort of examples of using seismic to at least track the geometry of the plume or the pathway.
Yeah, absolutely. I mean, don't get me wrong. We're not going to leave behind 2D and 3D classic industry seismic. That's my bread and butter. I'm addicted to this stuff, so I wouldn't leave that behind anyhow. But just to know where you are, you have to have these things. But I think from my talk, it should be clear that we need to have extra geophysical tools at our fingertips, and we have to collectively work on these. We have to get closer to the process. And to answer the question, we have to have 2D and 3D in the classic sense, but we have to have new geophysical tools to be employed as well.
I agree. It's very much an applied geophysics problem. There's a question from Thais Candido asking more on the log scale, which proxies or which parameters would you look at in the well logs to identify a possible hydrogen reservoir? I guess it might be more than just porosity.
Yeah, there are some papers on this, like a paper published on the Burakebugu field. Maiga, a gentleman who got his PhD in Paris, And then he very nicely describes what you can get out from the log character using density, neutron, and a combination of things. So there is some work already which shows what you need to look for, given the fact that it has been calibrated in Buroke-Boku.
Yeah.
If you send me an email, I can send you that paper specifically.
That's very kind. Quickly moving on if I can, we have a question from Fadin Nader saying, thank you for a great presentation, but asking a question regarding slide 29. The hydrogen seeps in the center of the Vienna Basin. Can they be related to naturally fractured rocks, discrete fracture networks? I guess you did show that, but on a smaller scale, I guess is the question.
Well, it's a very good question. Personally, I think that some of these big faults we have here, they conduct gases. And we know that because we find a lot of methane associated with these big faults. But it seems like, and this is just an impression, again, we have to look beyond the noise which is coming from all these false signals, that I personally believe that the hydrogen is really following these highways, these really big faults. Some of these faults have an offset of 3-4 kilometers. They are humongously large normal faults. And so the answer is yes, that if you have, I wouldn't call it fracturation, but intense tectonic deformation with large faults included, then you should expect a pattern of migration which is very specific to hydrogen. Hydrogen tends to latch onto the faults much more than natural gas because of its mobility.
Yeah.
I'm making it very, very simple. I apologize.
Well, I guess it's a smaller molecule, so it can make it through smaller gaps.
That's right.
We have a question from Carlos Davila asking, and this is a tough one too, even in the oil and gas sector, but how can we differentiate between leaking and sealing or low transmissibility faults and fluxing and leak potential, I guess, along fault planes?
Very good question. And this is a new field ahead of us because we in the oil and gas, we spend a lot of time on the fault seal analysis, okay, for obvious reasons. But now for hydrogen, we're going to have fault leak analysis ahead. And because we need to look for fault architectures which are favorable for acting like highways. And there's a lot of work done on this fault architecture coming from the point of view of we don't want to have leaking faults. So some of the literature and the great work done by a lot of structural geologists could be relooked and could be recycled not in a bad way to address these things. That what are really the favorable faults which could conduct most efficiently a hydrogen.
Fair enough.
Fault leak analysis, I think, is the new field we should call it.
Yes. And there's a somewhat related question from Pieter van Heinigen asking, what needs to be done to seismic data to see disturbance by H2? And I'd translate as other enhancements that can be done to illuminate those fault transmissibility parameters, perhaps.
I think when I look at any gas on seismic, and we know how that goes, the DHIs and the bright spots and blah, blah, blah. I don't think we'll be able to see a big stunning difference between natural gas signal versus a hydrogen signal, because they are both gases for the seismic method. So that's my gut feel. I might be wrong with this, and I hope somebody will be a little bit smarter than this and then start to see some physical differences which manifest themselves differently in the seismic. But at the first glance, I don't see it's going to behave differently. Now, imaging the fault planes, that's a classic problem, and that's going to stay with us. The better we can image a fault plane for oil and gas or natural gas or carbon sequestration or helium or geothermal for that matter, the better. So there's a room for improvement no matter what, regardless of hydrogen exploration.
The first thing that comes to my mind is there might be a density difference between natural gas accumulation and hydrogen accumulation.
Yeah, it could very well could be the case. There is a paper by an Australian colleague published just recently in a wonderful book on natural hydrogen. And then he's using some examples from the Officer Basin. That his examples are the DHI and then those things. And you might be right that the physics might give us a clue to make a little bit of a differentiation once we get that far.
Mm. And it's quite nice. Some of these questions are falling into certain categories. We have Ranin Belahassan asking, how can we determine whether serpentinization has occurred or is likely to occur in the future? What indicators could we use to assess that?
Yeah, very good question. And I put some slides into this presentation, but I took them out, and even with this I overrun. But there's a lot of work done on how you can guesstimate the level of serpentization using geophysical parameters. As you might have appreciated, is that density, susceptibility, shear wave versus longitudinal wave proportions. There are a lot of things which could be used to guess how much the serpentinization went ahead. For example, if I pick up a rock here in Austria, a very heavy rock of ophiolite, and then the density is 3.2, bulk density that is, that it didn't see much serpentinization just yet, like 5–10%. But if I pick up the serpentinite, which has just 2.5 or 2.6, that has been exhausted. So very simple and very powerful compilations were done, statistically speaking, to show the relationship between susceptibility, serpentinization, density versus serpentinization. So there are indirect ways, statistical ways of guessing how much the serpentinization went ahead.
Yeah, and I believe there's that susceptibility change with serpentinization. It can be very strong. So I remember prospecting for ultramafic and serpentinization zones in Australia a while back.
Exactly.
And now there's a question from Perth, Australia. It must be getting late there, asking if a conventional oil and gas field could produce both oil and gas and also hydrogen. I think you did touch on that subject during your presentation, but if you could expand on that, perhaps.
It did happen in the past, like I mentioned, Ukraine and former Soviet Union, let's just call it. And then the story, just briefly, is that when I was a kid, I'm Hungarian, and then in the 70s, and then there were this big, and they are still there, these pipelines, the Friendship and many other pipelines. And there are records of those pipelines bringing 1% or 2% of hydrogen, and then 1% or 0.5% helium. So there were fields in the Soviet Union at that point, including the Ukraine and Russia, which were co-producing hydrogen with natural gas. And they knew that this is the case, but at that point, nobody cared to separate or look at hydrogen on its own. But to answer your questions, there could be cases where hydrogen coexist with natural gas in a field which we already have, or already produced, or hopefully we're gonna find. I hope it's an answer.
Yes, just continuing on in that vein, I think you touched on the fact that in your worldwide map of hydrogen occurrence that there was much more found in Russia, but that's perhaps circular because they were testing for it as well. Because they had, at least in the past, a different model of hydrocarbon generation, thinking it was more geologically generated rather than kitchens of sedimentary rock.
Yeah, I mean, again, I'm from this part of the world, former Eastern Europe, if you will, and in general, the level of examination or analysis of gases involved a much broader spectrum of elements. And so it happened that they measured argon, neon, and all the rest, hydrogen and helium, which, and I'm not trying to pick on anyone, but for example, in the US, people were much more practical about oil and gas exploration, and they just wanted to find oil and gas, and that's it. But this, in a retrospect, gives a little bit of advantage to the former East, if you will, because these data sets are certainly there, not thinking ahead, but just happen to be the case. So you have richer data sets to start out with, and this is just the way it goes.
Fair enough. There's a question here from Maha Ali Haider asking, well, he's stating mostly, as most of the papers talk about the amount of hydrogen reported, but none of them seem to confirm its source of generation. Most of them seem to speculate it's from serpentinization or radiolysis. Could you comment a bit further on that?
In general, it's very interesting to see that the process of serpentinization did see a lot of work historically. A lot of very, very good work by academia. So for decades going back, if you Google for the serpentinization, you get thousands of excellent papers, as opposed to crystalline rocks and radiolysis, which just came on the radar screen, let's say, I don't know, I'm just making very simple, in the last decade or two. Yet the gut feel of mine and some other people smarter than I am is that even though the serpentinization had much more limelight and it's better understood, but given the fact that spatially ophiolites are not so much on this planet as huge cratons, where the radiolysis might not be so well understood and might not be so fast or so powerful, yet the sheer volume of how much old proterozoic crystalline rocks full of with uranium and thorium tickings anywhere on this planet, perhaps at the end of the day, volumetrically, that will be the preferred place. But don't take this literally, because I think we have to keep an open eye, and we have to go after both ophiolites, serpentinization, and radiolysis generated. So I'm not here to tell you which one is better than the other. We just don't know.
I guess there's still work to do. One thing that did grab my attention is the Mali example. You were saying those were very old rocks and the dolerites, so maybe radiolysis could still play a role in that deposit.
The way I understand it is that the source of hydrogen in the Mali field is probably large degree radiolysis, although there is a chance that there are some mafic, ultramafic rocks somewhere in the basement. I don't want to say that I really know what is, but the fact that it's sitting on a craton is clearly a sign that there has to be an element of radiolysis in the generation, for my naive thinking.
Don't want to push our luck, Gabor. Are you happy to answer one or two more questions, and then we'll close up the question?
Sure.
Terrific. We have a question here from Pavan saying, great presentation. My question is, how far are we from integrating conventional well log interpretation workflows into the natural hydrogen exploration process? And do you think the petrophysical signatures of hydrogen can be effectively distinguished from other gases in the borehole data? That might be a challenge, to my thinking.
It is a challenge, indeed. I mean, I described the log character. I mentioned the log character earlier in terms of the Mali field. And there are some good papers about the drilling-induced hydrogen signal. And we even published a paper, but many other people already noted this, is that if you drill, in many times you do have a hydrogen generated by the drill bit metamorphism, people call it. And you have to be very careful to distinguish that from the real geologic signal. And there are some, again, you have to do certain things. You have to look at other gases in the process. Now, about petrophysics, I think, to me, petrophysics, of course, will have to play a role because the reservoirs we have seen associated with the hydrogen. We'll have to host the hydrogen. It's going to be easier, more forgiving than hosting oil, for example. And then the petrophysics is already very important to define what is a good seal holding back the hydrogen. And I mentioned about the super seal evaporites. We know that, we love that. But how about these dolerites, which are in Borokotogú? And how come these turn out to be such good seals? And perhaps we should look for seals. We typically don't do that in terms of seals as seals. I'm sorry, it's a little bit silly statement, but volcanic subhorizontal injections being the seals for a petroleum or hydrogen system. So petrophysics will have to have a close, really good look at, for example, these volcanic intrusions as seals.
Yeah, I like your focus on the seals, because I think some of the examples you showed with looking for them underneath the evaporites or the salt might be a viable way of going after them here. Okay, I'd like to just pose one more question before we overstay our welcome with you. And I think it's an appropriate question to finish with. It's asking more about, and this one's from Mattia De Luca, asking how and when could we establish the hydrogen being continuously available in certain places becomes economically viable for exploitation? And that's a tough one, I think.
Yeah, I mean, I wish it would have happened. It's very hard or next to impossible to make a business case. And it's a very good last question for that matter, because for companies, mid-sized companies like mine or large companies Anthony's working for, it's very hard to put a hydrogen project on the table because the boss will ask you immediately, so who is making money doing this? Just show me an example. And we don't have an example at this point of time. So in my personal book, obviously the startups, smart people, Coloma and many people in Australia who are doing a wonderful job of trying to break the code. And one of them will come through, and I'm just waiting for that moment where I can pick up the newspaper and see that so-and-so made a big discovery, and it's clearly a money-making exercise, economic insights, and then the production will start, and then this and that and the other, because that will be the point when the floodgates will open. And we all want to do a natural hydrogen exploration, including mid-sized companies or large, classical, strong international companies. But until then, we have to wait, and then we just have to hope that again somebody will make that critical discovery.
Yeah, I guess there's nothing like a working money-making case study to motivate further investment or exploration. Well, with that, thank you very much, Gabor, for a wonderful presentation. Lots of very interesting questions. There's obviously a lot of interest in this subject. So thanks to you, thanks to Laurie for help facilitating this and the SEG, and of course the audience for participating and asking questions and for attending today. So with that, I'd like to thank everybody again and close this webinar for today and look forward to the next one.
Thank you, guys. Thanks a bunch and all the best. Take care.
Thank you, everybody.
Thank you. Bye-bye.